Hello friends, we are discussing about divide and conquer chapter. Okay, so we study next example of divide and conquer, that is one sorting technique, that is quick sort. Quick sort is other important sorting algorithm that is based on the divide and conquer approach. Unlike merge sort, which divides its input elements according to their position in the array, quicksort divides or partitions them according to their values. Okay, so quicksort is what one of the important sorting techniques. There are many sorting algorithms out there, so this is one important sorting algorithm. Okay, this is based on the divide and conquer approach. Okay, in merge sort, what we do is we divides its input elements according to their position. Okay, means half half. Okay, first half, second half, like this you do divides according to their positions. But in quick sorts, okay, we divides or partitions them according to their values. Okay, in merge sort we divides array elements according to their position, but in quick sort we divides or partitions according to their value. Okay, a partition is an arrangement of the array's elements so that all the elements to the left of some elements a of s are less than or equal to a of s, and all the elements to the right of a of s are greater than or equal to it. So here, so assume this is the value. Okay, the whichever the values which are less than this are left side, and the values which are greater than this a of s all are right side. Okay, based on this we divides. Okay, in quick sort. Okay, all the values which are less than a of s all are left side, which are greater than a of s all are right side. Okay, so like this we go on continuous. We'll see the algorithm. Okay, this is the quick sort algorithm. Okay, so here quick sort a of L to R means what, left to right. Okay, here left is the starting position, right is the last position. Sorts a sub array by quick sort. By using quick sort, we sort a sub array. Input sub array of array A from 0 to n minus 1. Okay, so you know array starts with 0. Okay, last position is n minus 1. Okay, so here inputs from a of 0 to a of n minus 1 elements defined by its left and right indices L and R. Okay, so L is starting, that is initially 0, then R is what, n minus 1 last. Output sub array A of L to R sorted in non-decreasing order. What is the output? It displays array elements in ascending order. If L is less than R, okay, if left position is less than right position, then partition S equal to partition of A L to R. S is a split position. S is a split position. Okay, which splits in such a way that all the values of S which are less than S, okay, which are on left side. Okay, and all the values which are more than S, which are at right side. Okay, so in such a way it splits. Then quick sort A of L to S minus 1. Okay, so L left value, S minus 1 is what? Okay, this which you partitioned. Okay, that is S minus 1. Okay, not half. In the binary search we do half, no, not like that. Okay, so which are the values less than S all are left side. Okay, means from this is this array, which are all the values of L to S minus 1 all are less values than S, and from S plus 1 to R which are greater than S. Okay, in such way we do partition. Okay, so the partition function is very important. Let's see the partition function. Okay, here S is a pivot value. Okay. Okay, this is the quicksort algorithm. The quicksort over. Next we will do the partition. This is also a very important function. Okay, this is partition algorithm. So here partition of A, L to R, left to right, partitions a sub-array by Horace algorithms using the first element as pivot. Okay, so here the first element is what? Pivot. Okay, so here this algorithm partitions a sub-array. Okay, so here first element is a pivot. Input sub-array of array A of 0 to n minus 1. Okay, so here what is the input? Array elements starting from 0 to n minus 1, defined by its left and right indices. Defined by left and right indices. L and R, left to L, right to R indices. L is less than R. L is what? Less than R. Output partition of A from L to R, starting from L last to R, with the split position returned as the function's value. So here the function value is what? Split position. Okay, in the array where it's split. Okay, so initially pivot value is A of L. Okay, left value, that is P. Okay, pivot value. Then I is equal to L. I is also L. Okay, L is the position, A of L is the value. Okay, P is the pivot value. J is equal to R plus 1. J is equal to R plus 1, right plus 1. Means the last position plus 1. Repeat, you have to repeat until I is greater than or equal to J. Okay, you have to repeat this loop until I is greater than or equal to J. Okay, if I is less than J, then this loop continues. Okay, when I is greater than or equal to J, then loop stops. So within that, one more repeat statement. Repeat I is equal to I plus 1 until A of I greater than or equal to P. Okay, so here you have to increment I is equal to I plus 1 until A of I greater than or equal to P. Okay, then so one more loop, repeat J is equal to J minus 1 until A of J less than or equal to P. Okay, you have to repeat J is equal to J minus 1. You have to decrement J value until A of J less than or equal to P. So here you have to increment I value until A of I greater than or equal to P. Okay, then after this both the loops false. Okay, then you have to swap A of I and A of J. Okay, you have to swap A of I and A of J. Okay, then after completion of this outer loop, okay, so when I is greater than or equal to J, okay, then you have to stop this loop. Okay, stop this repetition. Then you have to swap A of I and A of J. You have to swap what? A of I and A of J. Then also you have to swap A of L and A of J. Okay, you have to swap first A of I and A of J. Then you have to swap A of L and A of J. Then finally you have to return J. J is the position. Okay, J is the split position. Okay, note that index I can go out of the subarrays bonds in this pseudocode. We'll see the example, then it becomes very clear. Okay, consider this example. There are 8 elements are there, starting from A of 0 to A of 7. Okay, total 8 elements. First element 5, 3, 1, 9, 8, 2, 4, 7. Okay, so initially P is equal to A of L. Okay, initially L is 0, so P is equal to A of L, that is 5. P's value is how much? 5. Then I is equal to L. Okay, I is equal to L, that is 0. Then J is equal to R plus 1. Okay, J is equal to R plus 1 means right plus 1. Okay, L means left. So repeat. Okay, there are 3 loops are there. repeat. This is the outer loop, and there are two inner loops are there. Repeat I is equal to I plus 1 until a of I greater than or equal to p. Okay, you have to repeat I is equal to I plus 1, you have to increment I value until a of I is greater than or equal to p. Okay, when a of I is greater than or equal to p, okay, then you have to stop the loop. Okay, if a of I is less than p, then every time you have to increment I value. Similarly, you have to decrement j value until a of j less than or equal to p. If a of j is less than or equal to p, you have to stop the loop. If a of j is greater than p, then you have to decrement j value. Then you have to swap a of I and a of j. If both the loops are false, after this loop, you have to swap. Okay, this outer loop repeats until I is greater than or equal to j. If I is less than j, again it repeats. Okay, go on repeats. Okay, there is one outer loop and two inner loops are there. Okay, then you have to swap a of I and a of j, then swap a of L and a of j. Okay, at the end you have to return j value. Okay, so consider the example. Okay, these are the example. Initially p is equal to a of L. Okay, that is 5. Okay, and first here you have to increment I. Okay, repeat I is equal to I plus 1. Okay, so I points to here. Okay, initially it was here. Now I get increment point here. Okay, then check the condition. A of I less than p. Okay, if a of I less than p, less than 5, 3 is less than 5, yes, then you have to next you have to increment I. Okay, next I points here. Okay, 1 is less than 5, yes. Okay, then I points here. Okay, I points here. Then 9 is less than 5, no, 9 is greater than 5. If 9 is greater than 5, okay, then you have to stop this loop. If a of I is greater than or equal to p, then you have to stop the loop. Okay, then decrement j. Okay, j points here. Okay, so decrement j. So j points here. Initially j is here. Okay, with decrement points here. Okay, 4 is greater than 5. No, false. 4 is less than 5. Okay, if it is 4 is less than 5, a of j less than p, then you have to stop the loop. Okay, then you have to exchange a of I and a of j. Okay, you have to exchange what? A of I and a of j. This is j position, this is I position. So 9 comes here and 4 comes here. I and j get exchanged. A of I and a of j get exchanged. Okay, 9 comes here, comes here. Okay, then again. Okay, so what happens here? After swap, just check I is greater than or equal to j. What is I here? I is 0.23. I value is 3. J value is how much? 6. 3 is less than 6. Okay, 3 is less than 6. Then here if I value greater than j, then you have to stop. So here 3 is less than 6. Okay, so again you repeat the loop. Okay, so again I points here, though I increment here. I points here. Okay, so see here in next again loop get repeat. I increment to I plus 1. Okay, then check a of I is greater than p or less than p. Okay, a of I is how much? I incremented, no, I comes here. Okay, so 8 is less than 5, false. 8 is greater than 5. If 8 is greater than 5, then stop the loop. Okay, then decrement j and a of j less than p. So decrement j points here. 2 is greater than 5, false. 2 is less than 5, yes. Okay, if 2 is less than 5, you have to stop the loop and exchange a of I and a of j. Exchange a of I and a of j. So 2 and 8 exchange. 2 comes here, 8 comes here. Okay, again. Okay, so what happens here? After exchange, again check. I is greater than or equal to j. So I value is how much? 4. J value is how much? 5. Okay, so 4 is less than 5. Okay, again loop get repeats. Okay, so again loop repeats. So here I is equal to I plus 1. I get increment. So I was here, now I points here. Okay, Now check 8 is less than 5. No, 8 is greater than 5. Okay, if 8 is greater than 5, okay, so stop the loop. Okay, then next decrement j points here, decrement j comes here. Okay, j value is 4, I value is 5. So here then check a of j less than p. 2 is less than 5. Okay, 2 if 2 is less than 5, stop the loop. Okay, 2 less than 5, stop the loop. Okay, less than 5, stop the loop. Then swap a of I and a of j. So here what happens here, j become I become more than j. Okay, I become more than j, I is greater than j. Okay, if I greater than j, what to do? You have to stop the loop. You have to stop the outer loop. I is greater than j, stop the loop. Okay, then you have to exchange a of I, a of j, and a of l, a of j. So means what? What happens here? A of j, a of, so 5, 2 comes here and 5 comes here, exchange. Okay, a of j and a of l get exchanged. A of j and a of l get exchanged. Okay, so 5 comes here and 2 comes here. Okay, when this 5 comes here, we can check all the values less than 5, all are left side. All the values greater than 5, all are right side. So 5 is in the correct position. Clear? No? Okay. Next time what happens? Okay, this become okay, I value, this become j value. Okay, left side. Okay, again here this I, this j. Again it continues. Okay. Next time what happens? 2 place in the correct position. Okay, like this. Okay, like this it go on repeats. Clear? No? So finally all the elements in sorted order. Okay. So this is how this loop will work. Clear? No? Partition. Next analysis. There are 3 cases: best case, worst case, and average case. Okay. So here, first one, best case. Here the basic operation is key comparison. Okay. So main thing is what you are comparing. Okay. I is less than j, or a of I less than that number means okay. So main is the comparison. Okay. First you first this loop, here also you compare a of I greater than or equal to p. Okay, it more continuously compare until this condition satisfies. Okay, so here also you comparison, so here also comparison. Okay, so main thing is what? Comparison. Number of key comparison made before a partition is achieved is n plus 1 if the scanning indices cross over, and n if they coincide. Okay, so number of comparison made before partition is how much? N plus 1. Okay, if the scanning indices cross over, and n if they coincide. Okay, and number of comparisons is n if they coincide. If all the splits happens in the middle of the corresponding subarray, we will have the best case. When we will have the best case, okay, if all the splits happen in the middle of the corresponding subarrays, then it is the best case. Okay. The number of key comparisons in the best case satisfies the recurrence C best of n to C best of n by 2 plus n for n greater than 1. Okay, if n is more than 1, so this is the recurrence relation. Okay. For best case, if it is only one element, say though there is no comparison, so only 0 is the. So according to master theorem, C best of n belongs to theta of n log n base 2. Okay, solving it exactly for n is equal to the power of k yields C best of n is equal to n log n base 2. Okay, according to master theorem, C best of n is equal to n log n base 2. Okay, next, worst case. In the worst case, all the splits will be skewed to the extreme. One of the two subarrays will be empty. Okay, one array will be completely empty. Okay, there is no exact division here. Okay, one is full empty, one is okay. So it's become worst case, and the size of other will be just 1, less than the size of the subarray being partitioned. Okay, other is just 1, less than the size of the subarray being partitioned. This unfortunate situation will happen in particular for increasing arrays. So here in worst case, the total number of key comparison made n plus 1 plus n, that is the n plus 1 into n plus 2 divided by 2, okay, minus 3 belongs to theta of n square. Okay, so here there are two loops are there. Okay, so n into n, it's become what? N square. Okay, so this it take more comparisons. Next, in average case, let C AVG of n be the average number of key comparisons made by quicksort on a randomly ordered array of size n. A partition can happen in any position. 0 less than or equal to s less than or equal to n minus 1. Partition can happen in any position. Okay, in best case, exactly in the middle. Okay, so in worst case, okay, one subarray is empty. Okay, but in average case, the partition may happen anywhere in the array. After n plus 1 comparisons are made to achieve the partition. After the partition, the left and right subarray will have s and n minus 1 minus s elements respectively. Okay, so here, assuming that the partition split can happen in each position s with the same probability 1 by n. So we get the following recurrence relation. Okay, the recurrence relation is equal to C of AVG of n is equal to 1 by n, s equal to 0 to n minus 1, n plus 1 plus C AVG of s plus C AVG of n minus 1 minus n for n greater than 0. For n greater than 0, okay, so this is the recurrence relation. Okay, C AVG of 0 equal to 0. If there is no element, then it is 0. If it is only one element, then also it is 0. Its solution, which is much trickier than the worst and best case analysis, turns out to be C AVG of n equal to 2n log n base 2, means 1.39 n log n base 2. So means what? The average quicksort makes only 39% more comparison than in the best case. Okay, 39% more comparison than the best case. Moreover, its innermost loop is so efficient that it usually runs faster than merge sort on randomly ordered arrays of non-trivial sizes. Okay, that innermost loops run faster than the merge sort. This certainly justifies the name given to the algorithm by its inventor. Then there are some limitations. Of quicksort. It is not stable. Okay, quicksort is not stable. It requires stack to store parameters of subarrays that are yet to be sorted. Okay, so it requires what? Stack to store parameters of subarrays that are yet to be sorted. Okay, which are not sorted, that are in stack. Okay, so you have to need to store the elements in stack. While performance on randomly ordered arrays is known to be sensitive, not only to implementation details of the algorithm but also to both computer architecture and data type. Okay, so these are the limitations of quicksort. Okay, thank you.